What is going on, everybody, and welcome to a video on the Python Plays GTA series. Just want to go through some of the code aspects of the Charles 2.0, as well as address some of the frequently posted comments. So, first thing I want to do is I'm just going to drag up the tensor board. This is the training cycle. I actually ended up having to train this model twice. The first time I forgot to save the model. Yeah, I was pretty angry. Anyway, really, this one took 24 hours. So like just one whole day, and that's 24 hours per epoch. And all I did was train this model for one epoch. And I went that way because, at least with MobileNet, I trained that for multiple epochs and then went back and saw how each epoch did over time in terms of validation accuracy. And after one epoch, validation accuracy did only one thing, and that's go down. So with exception, I honestly have not run it beyond one epoch, looking at validation accuracy and validation loss, especially, like all validation loss is done has gone up after, I don't know, a third of training. So after that, like this looks like it's about to start coming down anyways, plus validation loss isn't continuing to drop. So I only did one epoch. At some point, I may end up pushing this model a little further just to see, but I don't think it's going to do any better. So really only one epoch. A ton of training data though, and yeah, that one epoch took 24 hours. So anyways, yeah, cool. So that's the model that we're using, exception. MobileNet, you can kind of see how MobileNet compared to exception. Very, very close in terms of their performance. Just a little different, like exception dropped quite quickly with the loss. Let me just refresh it so we get both. I don't know, why is this graph like all goofy? I guess because it's the validation loss, but if I unsmooth it anymore, you can't see these main ones. But you can see here that exception was just slightly better the whole time in all of the metrics that you can track. So, or at least all the metrics that we tracked. So anyways, exception it was. So next thing I want to talk about is, well, one thing was for sure the image pre-processing, just divided by 255. So all of your image arrays need to get divided by 255. That's really simple. I don't think I need to show code for that. Just understand that that was one of the changes that got made. So now I'm going to pull up the GitHub. In fact, I can just full screen it and come to two files I just updated. One is the exception model itself, and the other one is this weighting distribution by class. So coming over here, this is just the setup for the exception model, because all you really have to do is just import it from Keras, and then you set the input shape for that first layer. And obviously you don't accept their weights. They do offer like pre-trained weights that you can use transfer learning with. I wanted to use all of my own data. I've got plenty of data. That wasn't an issue, so I didn't need to do transfer learning. Specify the shape, again, 270 by 480. This is quite a big resolution. If you want, you could take a picture. I should have one maybe even in here. Let me scroll down real quick. I don't, but I bet I do on cyber.io. I have an image of a 480, 480 by 270. Here you go. Yeah, so this is a 480 by 270 resolution, and if we just kind of like zoom in a little bit, I mean, I feel like at this resolution, you can see all the things that you really need to see in a model. Like I can tell that's a car and a bus, and this is a car. This might be a motorcycle, but it's so far off in the distance, I don't really care. I can tell these are cars. Traffic light is easily discernible, buildings, trees. I feel like a 480 by 270 is good enough. Also, the mini map is easy to read, whereas at 160 by 90, that's like impossible. And like this is clearly a bus, but what the heck is this? I really don't know. Is that a bench or is that a car? So I think that's a pretty good resolution. So we're going to go ahead and just continue with that resolution. Really, that's it. So, honestly, it's just use exception rather than inception v3. The next thing is the weighting class distributor. I'll come up with a better name at some point, but basically what it does is it distributes the weights it adjusts weights in order to effectively distribute classes evenly. So in the prepared prepare data set. Let's see. Oh, this is actually, I think this will be, that's the training data, but the actual validation data is something like, it's like 500 gigabytes worth of data. It's a ton of training data. I'm sorry, not 500 gigabytes, like 500 megabytes worth of training data. It's a few samples from each of the segments of things that we did. So I created some training data and other people had created some training data, and we kind of pulled them all together. I also created training data at different times. At one point I started using the speedometer to attempt to see if we could teach Charles like how fast he was going at a given time. But then also the waypoints weren't always there, but later we added the waypoints. So this model's been trained with waypoints, without waypoints, with a speedometer, without a speedometer, and then in all the other scenarios like at night, in the daytime, police, no police, and so on, storms, all that stuff. So this model has training and all that, and that's really why this model works without the like the GPS and stuff like that. And I suspect that's why this model performs much, much better. One of the things that a lot of people said is like, hey, this model goes way too fast. That's kind of the whole point. The whole point of the model is to drive erratically. Like, I don't know about you, but when I play Grand Theft Auto, I drive pretty darn erratically, and I think most people do as well. So the whole point of Charles is to drive like that. And some people are claiming he doesn't brake. Maybe you weren't here for the other models. This is interesting. I just noticed this. That can't be correct. I think I'm going to have to go in there and fix that. I wonder when that has to have come in. I gotta fix that. Anyway, sorry, I got distracted when I noticed it's 1.A. It must have just gotten hit or something whenever I was moving things. Anyways, some people are like, oh, he doesn't use his brake. He definitely uses his brakes. So if you tune into the stream or something, you can hear the squeal of his brakes when he's using them, and you can also just see he slows down considerably. This is probably the first model that actually uses its brakes, and it does quite heavily. And then as far as crashing into things, like I would say the previous Charles model was like, I don't know, avoided things 10 to 20% of the time, whereas this one 70% of the time. I mean, he's doing pretty good in my opinion. I guess that doesn't matter, but yeah. So the other thing that I did here is, so this script just goes through and just ignore that A. I'm going to fix it at some point. And then here's the decay. And then all it does is it goes through these, you start with weights of 1.0. And then this is just so I know which is which. Then also I have a close dict. Basically, this is keys that are close, right? So if the model predicts A, but it was meant to be a WA, that's better than if the model predicted a D and it was meant to be a WA, right? So I wanted to just know, as I adjusted the weights, if we were losing sight of also just being close to the right answer, because the theory, of course, is that the validation data is perfectly balanced, so all the classes should be predicted an equal number of times. And so the theory of this script is, let's adjust the weights until that's true, and if we do that, the end result will be a better model. And so anyways, this is another way of just kind of measuring, like, is that still happening? And then, of course, running it in game is the final test, right? Is this actually better? So anyway, here we just load in the model. We have this distribution dictionary. Then this is just for simple calculations, and then we just start going through the data. So again, like I said, you bring in the data. This is just opening the training files, which are raw data. So then here we div by 255. This is the answer. This is like the classification. We check the prediction. And then we are using weights because that's the whole point of this. So it's just whatever the output from the neural network was. So this is just an array, right, of this distribution of what it thinks the prediction is. So then we apply this NumPy array of weights. We just multiply it. So this is not new. We've been doing that since the very, very beginning. So if we go to testmodel.py and we scroll down, I am sure we will find it. Looks like this, yes. So again, same thing, model.predict, and then we just multiply that prediction by another array of weights. Now these weights I just adjusted by hand, and then would test it in game, adjust it again by hand, test it in game. And I just felt like there's got to be a better way than doing that, and so that's how I came up with this method here. So then all it does is, as it's iterates through all this stuff, it just kind of prints out both the new accuracy, or prints out the weights the real accuracy against the actual data, and then the closeness accuracy. So again, the closeness is just like, hey, if it was meant to be a W, but it says WA, we're going to say that's still worth like being 30% right. Okay. So you still take a hit, but it's not the full hit. So anyway, that's what this script does. So then I just ran this for like many iterations, and basically once you just run it, you can run it indefinitely, but if you just keep running indefinitely, it's just going to keep shaving weights off. But until things are pretty well distributed, you just want to keep on running it. Now, with exception here, I found a few things were curious, and I think it's still the case. I'm actually going to pull up. Or did I save them? I did save them. So yeah, so S, the brake, and SA, yeah, and SD. So all of these were indeed things that he just does not want to predict. So I actually would. I ran the script for quite a while, and he still was never issuing breaks. So then what I did was I just set these to 1,000, which is crazy because look how little these numbers are. They started at 1.0. And then I was like, dude, so I set it to 1,000. Well, actually, first I did 10, and then I did 100, and I was like, dude, it's still not breaking. I did 1,000, and then he starts to break. So anyway, I assure you he breaks. I've got data to prove it. But yeah, that required some huge weights. The other thing is once he gets in-game, this weight for go forward is just not enough. He doesn't move enough. So I just, after the fact, this was actually the only weight I manually adjusted after this distribution, but it was definitely necessary. This one just doesn't move enough. Okay, so those are all of the changes. I don't really think there's much more for me to talk about leading up to this point. If I have forgotten something, someone feel free to remind me. But what I'm going to be focusing on next is taking, or basically bringing back the object detection API from TensorFlow. So hopefully that is supported on TensorFlow 1.11. I just upgraded to 1.11, the new release candidate. So I'm hoping to continue with that throughout this project. We'll see how that goes. I seem to have just horrible memories of working with the object detection API. I hope it's better now, but I doubt it. Anyway, that's going to be the next thing I jump into. That way Charles can can exit the vehicle and all that. And then also we can begin to do, if there is no motion going on, we know we're stuck and we can get out of it and stuff. So anyway, that is everything, I believe. Like I said, if you've got questions, comments, concerns, suggestions, whatever you think Charles is dumb, let me know below. Or if you think Charles is awesome, and I will heart your comment. Anyways, that's it for now. A quick shout out to the recent sponsors. We got two Edwards. Edward McCain. I apologize. Doot Madian? I don't know. Joe Bastuli. I think I recognize that one as a second time. Maybe it is if people continue, I see their name again. I'm not really sure. And Edward William Sams. Thank you guys very much for your support. I really appreciate it. You guys let me do this kind of stuff, and it's probably the best job I could possibly have. So thank you guys very much. Anyways, that's all for now. The GitHub is messy right now. It's going to continue to be messy. Other things people did talk about was like, you should have joystick control. Trust me, we did it before. I'll probably do it again. The problem is it makes some things better and then some things worse. So if with the joystick control or like any sort of degree control, it does slow him down quite a bit. So he won't go like full speed all the time. The problem though is when he doesn't go full speed, he turns early for many turns, because in the training data, I went full speed. I drove very erratically. So if he slows down, as he approaches turns, and if you've been following the stream either before or even now, this is still a problem. If he's not going very fast, he still tries to turn early for a turn as if he's going fast and he's going to slide out a little bit. And so that's kind of a problem. So I'm not really sure how we're going to overcome that, but I may bring back in the joystick control. But the next thing I really want to focus on is object detection. Really got to get object detection back so we can get him back stealing cars. When he loses a car, we can take away the invincibility. And then we can also have him do a lot more things like interact on foot and stuff like that. So that's definitely what I want to do next. So I got to start collecting data and all that. It'll be a hoot and a half. So anyway, for like the 19th time, that's it. Questions, comments, concerns, whatever, feel free to leave them below. Otherwise, I'm going to see you guys in another video.